Pluto, the dazzling planet living at the external edges of our nearby planetary system, is stirring up excitement within the vast cosmos. Reports indicate a possible encounter with Neptune, raising concerns among astronomers and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this celestial conflict. But how did Pluto end up on a collision course with its distant neighbor? And what could this impending crash mean for us here on Earth? Let's examine this unfolding event. Once considered a definitive planet, Pluto was later reclassified as a dwarf planet due to its unusual orbit. Despite this change, it continues to captivate and intrigue space experts. Continuous observations from leading scientists highlight a striking proximity between Pluto's orbit and that of Neptune. These experts warn of a potential collision between the two planets, presenting a significant risk to Earth. Pluto's journey around the Sun is marked by its extraordinary characteristics within our solar system. Its orbit spans an astonishing 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its uniqueness, Pluto's orbit is highly elliptical, differing from the nearly circular orbits of the major planets. Additionally, its orbit is tilted at a 17 degrees angle to the ecliptic plane, making it more inclined than most other planets. One notable feature of Pluto's orbit is its intersection with Neptune's path. For nearly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions about their relative positions in the solar system. So, why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The study of Pluto's orbit began soon after its discovery, presenting a puzzling challenge for astronomers. Unlike most planets, whose orbits align closely with the ecliptic plane, Pluto's distinct features include a steep inclination and an eccentric orbit. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit, despite these complexities, serves as evidence of the intricate nature of celestial mechanics. The three-body problem in space involves calculating the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This issue explains the complex interplay of their orbits and gravitational forces. Terms like AML libration and the Kozai effect help unravel this cosmic mystery. Astrophysicists argue that libration, responsible for maintaining planetary orbits, plays a crucial role in the Pluto-Neptune system. This term refers to the fact that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune, effectively preventing potential collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it remains primarily aligned above or below their orbital plane, providing an extra layer of protection against impacts. The Kozai effect explains why Pluto's orbit around the Sun appears irregular, but remains stable over long periods despite apparent anomalies. Mathematical simulations in the late 1980s revealed that, despite its stable properties, Pluto's orbit is technically chaotic. Even slight initial deviations can lead to vast changes over long time scales. However, Pluto's unique orbit maintains stability over incredibly long periods, keeping variations within limits. Continuous virtual simulations have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path. Near the Sun, Neptune's special relationship with Pluto, completing 3 orbits for every 2 of Pluto's, adds to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a significant influence, while Saturn's effect, though smaller, also plays a role. Through extensive studies, scientists have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the secure and stable movement of Pluto in space for billions of years. These phenomena are crucial for maintaining order and consistency in celestial mechanics. Without these stabilizing mechanisms, the solar system would be prone to greater chaos, potentially leading to planetary collisions or ejections from stable orbits, with inevitable consequences for other celestial bodies. Understanding Pluto's orbit is particularly important in discussions about a potential collision with Neptune in the future. This knowledge provides a clearer insight into the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can achieve balance through the intricate interplay of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a deeper understanding of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The nature of orbital mechanics vividly demonstrates the delicate dependence of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the dwarf planet's position or velocity can significantly alter its long-term trajectory. Computer simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, astronomers can observe how even minor changes can have a massive impact on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit. Despite factors like AML libration and the Kozai effect contributing to its stability, Pluto's orbit can still exhibit chaotic behavior. Even a small initial difference in Pluto's position or speed can lead to significant changes in its orbit over many years. Nonetheless, despite this inherent instability, Pluto's orbit remains stable over extremely long periods, spanning billions of years. This suggests that beneath its seemingly irregular nature, Pluto's journey around the Sun follows a precise cosmic order. Predicting celestial events, forecasting the future paths of celestial bodies, especially planets like Pluto with unusual orbits, is incredibly challenging. The inherent unpredictability of these systems makes long-term predictions uncertain. Mathematical simulations help us understand and estimate the future movements of celestial bodies, but they also reveal the limitations of our predictive abilities. These models heavily depend on accurate initial conditions and simulate complex interactions, where even a tiny error can lead to vastly different outcomes, making precise predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made great progress in understanding space, Pluto's case highlights the limitations of our current knowledge. While Pluto's orbit remains stable over billions of years, scientists continue to study whether external factors, such as gravitational perturbations from other planets or passing celestial bodies, could eventually alter its trajectory. Given its highly elliptical and inclined orbit, Pluto is more susceptible to external gravitational influences than the major planets. One key area of interest is the long-term stability of Pluto's 3:2 resonance with Neptune. As previously mentioned, for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This gravitational synchronization ensures that Pluto never collides with Neptune. However, the question remains, will this resonance hold indefinitely, or could disruptions arise over extremely long timescales? The role of the Kuiper Belt and distant gravitational influences. Pluto is a member of the Kuiper Belt, a vast region of icy bodies beyond Neptune. Many Kuiper Belt objects, KBOs, share similar orbital characteristics with Pluto, leading astronomers to classify them as plutinos, a subclass of KBOs that also follow a 3:2 resonance with Neptune. As Pluto and other plutinos orbit the Sun, their interactions with each other and with Neptune play a crucial role in shaping the overall structure of the Kuiper Belt. Some scientists speculate that a previously undetected large celestial body, often referred to as Planet 9, could be influencing the orbits of Kuiper Belt objects, potentially affecting Pluto's long-term stability. If such a massive distant planet exists, its gravitational pull could subtly alter Pluto's orbit over millions of years. However, current observational data has not confirmed the existence of Planet 9, and its potential impact on Pluto remains a subject of active research. Could Pluto ever escape the solar system? While it is highly unlikely in the foreseeable future, some theoretical scenarios suggest that Pluto could be ejected from the solar system under extreme circumstances. Such an event could be triggered by a close encounter with a rogue planet or a passing star exerting a strong gravitational pull on the outer solar system. Simulations show that in rare cases, Neptune's gravitational influence on Pluto could be disrupted by external forces, leading to orbital instability. If this occurred, Pluto could either spiral closer to Neptune, increasing the chances of a collision over an enormous timescale, or be flung outward, becoming a rogue planet wandering through interstellar space. Although this scenario is highly improbable, it highlights the intricate gravitational dance governing Pluto's motion. What would happen if Pluto and Neptune collided? If a collision between Pluto and Neptune were ever to occur, it would be a catastrophic event, releasing an immense amount of energy. However, due to their size difference, Neptune would likely absorb Pluto, while Pluto itself would be completely shattered. The impact could result in the creation of a debris field in the outer solar system, the potential formation of a new ring system around Neptune, minor alterations to Neptune's orbit, though not enough to destabilize the solar system, possible effects on nearby Kuiper belt objects due to gravitational disturbances. Thankfully, because of their synchronized orbits and orbital resonance, such a collision is extremely unlikely for billions of years. The bigger picture. What Pluto teaches us about celestial dynamics. Pluto serves as an exceptional case study in celestial mechanics. Its unique orbit provides insights into how planetary systems evolve and how gravitational interactions shape the motions of celestial bodies over time. The study of Pluto also contributes to 1. Understanding orbital resonances. The 3:2 resonance with Neptune helps explain how planetary systems remain stable over billions of years. 2. The nature of Kuiper belt objects. Pluto's behavior gives clues about other distant icy worlds, some of which might harbor subsurface oceans or organic compounds. 3. The search for Planet 9. Investigating Pluto's orbit may provide evidence for a hidden massive planet influencing the outer solar system. 4. Chaotic systems in astronomy. Pluto's orbit demonstrates how small perturbations can lead to significant changes over long time frames, a concept critical in predicting the behavior of exoplanetary systems. Conclusion. Pluto's enduring mystique. Although reclassified as a dwarf planet, Pluto remains one of the most fascinating objects in the solar system. Its dynamic orbit, interactions with Neptune, and possible influences from distant celestial bodies continue to challenge our understanding of planetary motion and cosmic stability. While concerns about a Pluto-Neptune collision may capture public imagination, astronomical studies reassure us that such an event is virtually impossible in any relevant time frame. However, Pluto's long-term fate, whether it remains in stable orbit, gets perturbed by an unknown force, or even escapes the solar system, will remain an area of continued exploration. As technology advances, future space missions and telescopic observations may provide even deeper insights into Pluto's complex journey through the cosmos. Until then, Pluto continues to remind us that the universe is full of mysteries waiting to be unraveled. The gravitational impacts of Goliath planets on Pluto's circle provide significant insights into the broader dynamics of the planetary system. It shows how the presence and position of each planet can affect the stability and trajectory of various bodies in the system. Notwithstanding these complex forces, prominent astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist, offers a remarkable perspective on the mysteries of our planetary system, particularly regarding Pluto. Tyson, known for reclassifying Pluto as a dwarf planet rather than a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson views Pluto's reclassification not as a demotion, but as an essential shift in accordance with our expanding knowledge about the diverse objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a testament to how much more there is to discover in space. Tyson believes that the allure of these mysteries is what makes astronomy so fascinating. Furthermore, Tyson is aware of how space-related events and discoveries capture the public's imagination. He sees events like Pluto's reclassification and its unique orbit as opportunities to engage public interest in the universe. By discussing the dynamic and sometimes chaotic aspects of space mechanics, Tyson promotes a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson sheds light on the wonders and mysteries of the universe. Working alongside other scientists, Tyson actively warns the public about the potential dangers of Pluto's unusual orbit. After extensive study of Pluto, he has raised concerns that the three-body problem could pose a significant threat, suggesting that a collision with Neptune may be long overdue. Moreover, Tyson emphasizes that such an impact could disrupt the balance of the solar system and lead to catastrophic consequences, possibly even extending to Earth. A collision between Pluto and Neptune would be a rare and devastating event in our planetary system. This impact would release an enormous amount of energy, likely shattering Pluto due to its smaller size and icy composition. Debris from the collision could spread throughout the nearby planetary region, posing potential hazards to other planets and their moons. For Neptune, such an impact could potentially alter its atmosphere and orbit, depending on the specifics of the collision. Michio Kaku, a well-known theoretical physicist famous for his work in string theory and science communication, offers a fascinating perspective on this scenario. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics provide valuable insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can aid in navigating the solar system more efficiently, anticipating potential hazards, and planning missions to the outer reaches of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to the exploration of other celestial bodies, providing a framework for approaching and understanding distant worlds. In analyzing planetary physics, Kaku often highlights the crucial link between celestial mechanics and theoretical physics. He believes that planetary movements and interactions, such as the gravitational dance between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to grasp these principles at their most fundamental level. He suggests that considering the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a spectacular event in astronomy, providing a rare observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. A collision of such magnitude in the nearby planetary system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extreme conditions. A key focus in string theory is also the gravitational waves generated by such an impact, which could provide valuable data for testing predictions related to gravity and space-time. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially advancing our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a crucial example of celestial mechanics, demonstrating both stability and disruption within our solar system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the complex and dynamic nature of space. The universe holds many mysteries, and the three-body problem is just one of them. There are other potential cosmic disasters that scientists anticipate. While the likelihood of planets colliding in space is extremely low, it is not entirely impossible. The way planetary orbits are affected by various factors, including gravitational interactions, is explained by the three-body problem. In some star systems, such as TRAPPIST-1, which hosts 7 Earth-sized planets, gravitational forces create a harmonic pattern known as orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. However, despite the compact nature of systems like TRAPPIST-1, collisions are not currently occurring. Scientists closely monitor these systems to understand how planets influence each other's orbits, especially when they are in close proximity. This knowledge helps us understand planetary formation and evolution in space. Rogue planets drifting through space without orbiting a star present another intriguing phenomenon. These planets, once part of a star system, are ejected due to gravitational disturbances or other celestial events. For example, the close approach of another star or dynamic instability in different systems can cause these rogue planets to travel vast distances, potentially entering regions far from their origin.